Hello dear students, today we are going to discuss atomic mass or atomic weight. In the previous class, we have gone through the concept of atoms based on Dalton's atomic theory. Once we have developed the idea or the concept of atoms, we need to find out the mass or the weight of an atom. So let's see what is atomic weight or atomic mass and what are the different scales used for measuring mass of an atom or atomic mass, and what are the different types of atomic mass and how they are related to each other. So we have atomic mass. Now we are going to define what is atomic mass. Now there are different masses that we use in chemistry, and different types of mass that we use in chemistry is relative atomic mass, or simply say atomic mass. Second type of mass that we use is absolute mass. Then we have gram atomic mass. Then we also have average atomic mass. So we have the relative atomic mass, or simply say atomic mass. We have absolute mass, we have gram atomic mass, and we have average atomic mass. So we'll define this each and every term and see the relationship between the various mass. So first of all, take up this relative atomic mass. Or simply say atomic mass. Now look at this. This relative atomic mass or atomic mass, there is a specific term used as relative. That means atoms being not visible to naked eyes. The saying is very easy to say, okay, we can easily find the mass of an atom, but in reality, measurement of a quantity which cannot be observed with naked eyes is not an easy task. So to define these atoms which cannot be observed with naked eye, we measure the mass of those substances with reference to another standard mass. So since the measurement of the mass of atom is with respect to another standard substance, so the word relative stance means this is measured with respect to the mass of another standard substance known. That mass is what we call as relative atomic mass, or simply we say this is atomic mass. So for measuring this, we take the help of a standard reference. So by use of this standard reference, we define the mass of an atom is how much the mass of an atom or of an element is heavier with respect to the standard mass. So this relative atomic mass, so simple basic definition is this relative atomic mass is mass of an atom of an element divided by standard mass. So this ratio, mass of an atom of an element divided by standard mass. So this standard, that is what we call as the reference. So we are measuring the mass of an atom with respect to this standard. So while defining this atomic mass, we take the ratio of this mass. So look at this. So this mass of an atom of an element, this will be having some unit, divided by standard mass. So this relative atomic mass, or simply we say this atomic mass, this is not a mass. So point to be noted is not an actual mass. Why this is not an actual mass? If I say this is an actual mass, mass will have some unit, whereas this relative atomic mass is a ratio of two mass. Numerator is also mass, denominator is also mass. So the ratio of two mass will be a simple pure number without any dimension or unit. So this is not an actual mass because this is the ratio of two mass. This relative atomic mass is a pure number, and this doesn't have any unit. Pure number, no unit. So this relative atomic mass is simply a pure number. This relative atomic mass is measured always with reference to a standard mass. With the reference to a standard mass. So these are the points to be kept in mind while discussing relative atomic mass. So we are saying that this is the ratio of two mass of a given atom divided by mass. That is what we call a standard mass. So we have a ratio of two mass. So this cannot be a mass. This is simply a pure number without any dimension. And for measuring this relative atomic mass, we always require a standard reference. So now coming to the standard reference that is used for measuring this relative atomic mass. That means the scales used for measuring this atomic mass. So let's go back to the brief history of these scales used for measuring this relative atomic mass. The first scale is hydrogen scale. So for the very first time, this relative atomic mass was measured in terms of hydrogen. So this hydrogen was taken as a reference. So reference is hydrogen. So taking this hydrogen is a scale, this relative atomic mass is defined as mass of an atom of an element divided by mass of one atom of hydrogen. So hydrogen being the lightest element, being the simplest element, this hydrogen was considered to be the standard reference. So taking this ratio, we have the relative atomic mass which is defined in terms of hydrogen scale. Now later on, this hydrogen scale is removed by another scale. The cause for removal of this hydrogen scale is there is some demerits or drawbacks for using this hydrogen scale. Now the demerit or the drawbacks of using this hydrogen scales is hydrogen being the smallest and the lightest element, the exact measurement of the mass of hydrogen is very tough job. So one of the drawback is hydrogen being the smallest and lightest, its mass measurement becomes tough. The smallest, lightest element, so smallest and lightest element, so mass measurement not accurate. So this was one of the reason why we remove hydrogen by some other scale. Second demerit concerning this hydrogen scale is these hydrogen. So we take this hydrogen scale while measuring the mass of atom using this hydrogen scale, the atomic mass were found to be fractional values, whereas the experimentally defined atomic masses of most of the atoms were found to be whole number. So experimental values of the atomic mass of the given elements, atoms of elements were found to be whole numbers, whereas the mass that we measure by using this hydrogen scale comes out to be the fractional values. So there is a practical difference between the experimental value and the theoretical value that we develop based on this hydrogen scale. So second demerit is mass were found to be fractional. As I told you, experimental mass were found to be whole numbers, while the mass measured in terms of hydrogen scale were found to having the fractional value. So there is no correlation between the experimental value and the theoretical value. So this was another reason for removing this hydrogen scale by some other scale. So this was the first scale, hydrogen scale. Now to remove this discrepancy regarding this hydrogen scale, another scale was developed, and that scale is known as oxygen scale. The second scale is O scale. So for this oxygen scale, the most stable isotope of oxygen, that is O16, oxygen with isotopic mass 16, was taken as a standard reference for measuring the atomic mass of an element. Now based on this oxygen scale, the relative atomic mass, this is defined as mass of an atom of an element divided by 1/16 times mass of one atom of oxygen 16. So look at this, the relative atomic mass of this element in oxygen scale is mass of an atom of an element, which is to be defined, divided by 1/16 times the mass of one atom of oxygen 16, the most stable isotope of oxygen. So this ratio was defined as oxygen scale, mass in terms of oxygen scale. So now look at this. One of the important demerits of this hydrogen scale was atomic mass measured in terms of hydrogen scale was found to be having fractional values, whereas if you measure the mass in terms of oxygen scale, most of the mass were found to be having whole number ratio, whole numbers. So since most of the mass were having whole numbers, so this was more accurate than hydrogen scale. Second, in case of hydrogen scale, hydrogen and oxygen being more reactive than hydrogen, it's very easy to obtain these elements in oxide form rather than hydride form, because most of the elements cannot deal with hydrogen to give you hydride. Whereas oxygen being a very reactive, most of the elements present in the periodic table can easily react with oxygen to give you oxides. So it's very easy to obtain oxides rather than halides. So this was oxygen scale. And the third scale is carbon scale. Now, this is the latest or IUPAC recommended scale that we use in chemistry. So, whenever we talk of atomic mass, so that is carbon scale, that is the latest IUPAC recommended mass. So, in this carbon scale, the most stable isotope of carbon, that is carbon with isotopic mass 12. This is taken as standard reference. So later on we developed an instrument which is known as mass spectrometer. So this instrument, mass spectrometer, measures the mass of carbon 12 to be 12 unit. So based on this mass spectrometer, all these early scales, hydrogen scale, oxygen scale, this is removed by carbon scale. So we are going to define this atomic mass in terms of carbon scale. So based on this carbon scale, this relative atomic mass, this is defined as mass of an atom of an element divided by 1/12 times mass of one atom of carbon 12 isotope. So the relative atomic mass based on the modern scale or the latest scale or the IUPAC scale, that is carbon scale, is defined as mass of an atom of an element, of any element, divided by 1/12 times the mass of one atom of carbon 12. So this ratio is what we call as atomic mass. So whenever someone asks you what is atomic mass, so the definition is atomic mass is the mass of an atom of an element divided by 1/12 times the mass of one atom of carbon 12, or simply we can say atomic mass or relative atomic mass is the mass of an, means how much mass of an atom is heavier compared to 1/12 times the mass of one atom of carbon 12. So this is the basic definition for relative atomic mass. Now look at this, we have a term here, 1/12 times mass of one atom of carbon 12. So this term is defined as 1 atomic mass unit. Earlier we used atomic mass unit. Now latest IUPAC convention says this atomic mass unit should be replaced by unified mass U. So one atomic mass unit or one unified mass is nothing but this term, that is mass of one atom of carbon 12 divided by 12. So this term 1/12 times mass of one atom of carbon 12, this ratio is defined by one atomic mass unit or simply one unified mass. So this is unified mass, this is atomic mass unit. So now, so we replace this term by mu or simply U. So we have this relative atomic mass which is equals to mass of one atom of any given element divided by 1 U So therefore, mass of one atom of any given element, this is equals to the relative atomic mass multiplied by 1 U. So whenever we measure this mass in terms of carbon scale, the mass is always reported in terms of U unit or in terms of AMU unit. So otherwise, this is nothing but the ratio of 2 mass. So we should not have any value, physical unit is a unitless quantity, and 1 atomic mass unit or 1 unified mass. This is, so mathematically this is 1 by 12, and mass of 1 atom of carbon 12. This is 12 by Na, where this Na is what equal as Avogadro number, and it has got a fixed value, that is 6.02 into 10 to the power 23, that is known as Avogadro's number. So one unified mass or one atomic mass unit is equals to 1 by Na, Avogadro number. So Na is 6.02 into 10 power 23, and this value comes out to be 1.66056 into 10 to the power minus 24 gram equivalent. So the gram equivalent of one atomic mass unit or one unified mass is 1.66056 into 10 power minus 24 gram. So this is equal to 1.66056 into 10 to the power minus 27 kilogram. So in terms of kilogram, this is the kilogram equivalent of unified mass. So look at this, we have this mass of one atom is equal to relative atomic mass into one unified mass. So this is the atomic mass based on this carbon scale. So this is how we define atomic mass. So look at this. So if suppose atomic mass is given to and has to be converted into unified mass, then mass of one atom divided by gram equivalent of unified mass, that will give you relative atomic mass. So we have this relation. Now look at this. We say mass of hydrogen, this is 1.008 U, mass of carbon 12 U, mass of oxygen 16 U, mass of iron 56 U. So all these mass that is reported in chemistry literature books, these masses are always mentioned in terms of unified mass or atomic mass unit. So this is nothing but based on this carbon scale. So this is what we call as relative atomic mass. So why this is known as relative? Because this is measured with reference to a standard reference. That standard reference taken is carbon 12 isotope, that is the most stable isotope of carbon. So this is the relative atomic mass. So this was one force mass. Now once we know this relative atomic mass, then let's see what is absolute mass of an atom. Second mass, that is absolute mass. So this absolute mass is the exact mass, and this must be measured in terms of gram unit. The exact mass expressed in gram unit of one atom of an element. So what is the exact mass of one atom of an element? measured in terms of gram unit, that is known as absolute mass. So we have to define exact mass of one atom. So this absolute mass, let me define in terms of this AM. So absolute mass is equals to the relative atomic mass that we measure in first. So relative atomic mass multiplied by gram equivalent of atomic mass unit or unified mass. So the gram equivalent of unified mass is 1.66056 into 10 to the power minus 24 gram. So this is the exact mass of one atom of an element expressed in gram unit. So let's take this example. The relative atomic mass of hydrogen, this is given as 1.008 U. If this is the relative atomic mass of hydrogen, that is 1.6008 U, then the absolute mass of hydrogen is one atom of hydrogen. So this is the relative mass into the gram equivalent of unified mass. So this is 1.66056 into 10 to the power minus 24 grams. So this is the exact mass of one atom of an element in terms of a gram unit. Take this, the relative atomic mass of carbon. So this is 12 U. So therefore, absolute mass of carbon is 12 gram equivalent of unified mass, which is 1.66056 into 10 to the power minus 24 gram. So this is the absolute mass, that is the exact mass of single atom that must be expressed in terms of gram unit, and this is the relationship between the relative mass and the absolute mass. Now once we have this, the absolute mass and relative mass, the third mass that we often use in chemistry literature book is gram atomic mass. So, gram atomic mass. So let's see what is gram atomic mass. Now in chemistry we use a term which is known as 1 gram atom. So the meaning of this gram atom is 1 gram atom. This represents 6.02 into 10 to the power 23 atoms, which is equivalent to Avogadro number of atoms. So 1 gram atom in chemistry represents 1 Avogadro number of atoms, that is 6.02 into 10 to the power 23 atoms. So look at this heading, gram atomic mass. So from definition point of view, this gram atomic mass is defined as mass of 1 gram atom, that is mass of 6.02 into 10 to the power 23 atoms of a given element expressed in terms of gram unit. That unit mass is known as gram atomic mass. So I repeat, gram atomic mass is the mass of 1 gram atom, that is 6.02 into 10 to the power 23 atoms of the given element expressed in gram unit. That is what we call as gram atomic mass. So therefore look at this. This gram atomic mass is equals to absolute mass, that is the exact mass of one atom expressed in terms of gram unit. This is mass of single atom, whereas gram atomic mass is defined for 6.02 into 10 to the power 23 atoms. So multiply this absolute mass by 1 gram atom, that is 6.02 into 10 to the power 23, or simply we can say absolute mass into the Avogadro number of atoms, and this must be expressed in terms of gram unit, that is gram atomic mass. Now look at this. This absolute mass is relative atomic mass expressed in terms of gram unit. So therefore, look at this. Gram atomic mass is equals to relative atomic mass into the gram equivalent of unified mass. Now this gram equivalent of unified mass, that is equals to 1 by Avogadro number. So we have defined it. 1 U is equals to 1 by Na, which is equals to 1.66056 into 10 to the power 24. So we can replace this by 1 by Na into Na. This is in terms of gram unit. So this cancels out. So therefore, look at this. Gram atomic mass is equal to relative atomic mass but in gram unit. So what I'm trying to convey is that numerical value of gram atomic mass and the relative atomic mass of any given atom is always same, but there is a difference in unit. So this is how we derive. Gram atomic mass is relative atomic mass into gram equivalent of unified mass, that is 1 by Na, and gram atomic mass is defined for Avogadro number of atoms. So we have this. So numerical value of gram atomic mass and the relative atomic mass is always same. So take this example. The relative atomic mass of suppose carbon. So this is 12 U. Absolute mass of carbon, that is 12 by Na gram. This is equals to 12 into 1.66056 into 10 to the power minus 24 gram. Gram atomic mass of carbon, that is 12 by Na, that is absolute mass into number of gram atoms expressed in terms of G. So this comes out to be 12 gram. So the relative atomic mass of carbon is 12 U. Gram atomic mass of carbon is also 12, but there is a difference in unit. This is in terms of unified mass, this is in terms of gram. So this is gram atomic mass. So basically look at this. Gram atomic mass is mass of 1 gram atom, which is equals to 6.02 into 10 to the power 23, or Avogadro number of atoms expressed in gram unit, that is gram atomic mass. Now this is gram atomic mass. Once we have this gram atomic mass, there is one more mass to be discussed, and that mass is average mass. Average atomic mass. Now look at this, we have a particular term which is known as average. So that means this is the average of atomic mass. That will take the average of the atomic mass. So let's see what is the meaning of this average. Now most of the elements present in periodic table, has got some isotopes. In the previous lecture, I have given you what is the meaning of isotope. Isotopes are those substances having same atomic number but different mass number. So every element present in the periodic table has got some isotopic form. Take the case of hydrogen. So hydrogen exists in three different isotopic forms. One is known as protium, atomic number 1, mass number 1. Second form of hydrogen is deuterium, or known as heavy isotope of hydrogen. Atomic number is 1, mass number is 2. Then the third isotope of hydrogen is tritium, that is the radioactive form of hydrogen. Atomic mass number is 1, mass number is 3. So we have same element hydrogen existing in three different forms. First form protium, mass number 1. Second form deuterium, heavier isotope, mass number 2. Third form tritium, mass number 3. If I say express this is in terms of protium, we are ignoring the contribution of deuterium and tritium, which is not possible because in nature some of this hydrogen is found in form of tritium as well as in form of deuterium. So this deuterium and tritium should have some contribution. Similarly, if I take this mass of hydrogen to be these two, then we are ignoring the contribution of this protium and tritium. This is again incorrect. Similarly, if we express mass of hydrogen in terms of tritium, then again we are ignoring the contribution of these two other isotopes. So whenever we have these isotopes, we take the contribution of each and every isotope, and that value is defined as average atomic mass. So when in the first case, when we define this relative atomic mass, so that relative atomic mass is nothing but the average values of all isotopic forms. So if suppose this is the different isotopes, and let's say their percentage abundance. Percentage abundance means in what is its existence in nature. Let's suppose this percentage abundance is X. So protium in nature it is X%, deuterium Y%, tritium Z%. Then the average atomic mass of hydrogen is equal to summation of isotopic mass into percentage abundance divided by 100. So summation of this term, isotopic mass into percentage abundance of each and every component divided by 100. So take this first protein. Isotopic mass is 1. So we have this 1. Percentage abundance is X. 1 into X. Plus contribution of deuterium. Isotopic mass is 2. We have 2. Percentage is Y. Contribution of tritium. Isotopic mass is 3. 3 into percentage is Z. This is the meaning of summation of isotopic mass into percentage abundance divided by 100. So this will give you the average atomic mass of hydrogen, which was defined as 1.008 atomic mass unit. So this is the average atomic mass of hydrogen. So in a generalized form, if suppose an element A exists in isotopic forms A1 and A2, percentage abundance is, suppose this is X, this is Y, and isotopic mass. If suppose isotopic mass of this isotope is suppose A, this is B, then average atomic mass of this element A is summation of this isotopic mass into abundance. So isotopic mass is A, percentage is X, plus isotopic mass of A2 is B, percentage is Y, divided by 100. Now percentage divided by 100 comes out to be always a fractional value. So we can say this is also equals to summation of isotopic mass into fractional abundance. So look at this. So either we can define in terms of percentage abundance or in terms of fractional abundance. So fractional abundance is nothing but percentage divided by 100. That comes out to be the fractional abundance. So we have looked at these are the different types of atomic mass that we use in chemistry literature. So and I have shown you what is the definition, what is the actual meaning of the term different types of mass, what is the correlation between the different mass units. So once we have this, let's solve some numericals. Problem 1. Now look at this, we have this average atomic mass. We define this average atomic mass is the average of all the given components, that is the isotopes present in that given element. Look at this carbon, the element carbon. Let's assume if this element carbon is two isotopic form, that is carbon 12 and carbon 13, and the average atomic mass of carbon, suppose this is 12.01 U. Carbon existing in two isotopic form, this is just from calculation point of view, carbon 12 and carbon 13, and the average atomic mass of carbon is 12.01 U. Now we have to find the percentage of carbon 12. Percentage of carbon 12 in nature and percentage of carbon 13 in nature. You have to find the percentage. Now let's take this percentage of carbon 12. Let this be X, and the percentage of carbon 13, let this be Y. So the percentage means total number of parts is 100. So this Y will be equal to 100 minus X, because X plus Y should always be equal to 100. So we have this average atomic mass. Average atomic mass, this is summation of product of isotopic mass into percentage abundance. So look at this, what is carbon 12? That is isotopic mass. So 12 into its percentage X, plus 13 into its percentage, that is X, Y. Sorry, Y is equal to 100 minus X divided by 100. So we have given this average atomic mass as 12.01 into 100 is equal to 12x plus 1300 minus 13x. So therefore look at this, 1300 minus 1201 is equal to x. So we have isotopic mass percentage. Isotopic mass percentage divided by 100 is equal to average. Average is 12.01 into 100, 12x, this value. So x is equal to 1300 minus 1201. So therefore x is equal to 99. So in nature, 99% of the carbon is in the form of carbon 12, and the remaining 1% is for this carbon 13. So therefore percentage of carbon 12, that is X, is equal to 99, and the percentage of carbon 13, that is equal to 1, which is equal to 100 minus X, this is 1%. So this is how we define average atomic mass, and from the average atomic mass how we can define the percentage, or if the percentage is also given, then also we can define the average atomic mass. Let's take up one more example here. In nature, chlorine exists in two isotopic form. Chlorine isotopic mass 35, chlorine isotopic mass 37, and these chlorine 35 is percentage abundance is 75%, whereas the percentage abundance of this chlorine is 25%. Then what is the average atomic mass of chlorine? So we have isotopic mass, we have percentage. So simply we have to use the formula. So average atomic mass of chlorine is summation of isotopic mass into percentage abundance divided by 100. So look at this contribution of 35 into 75 plus 37 into 25 divided by 100. So this will give you the average atomic mass of chlorine, in which this is existing in 35 atomic mass or 37 with respective percentage abundance. So this is average atomic mass. Let's take up some more example. Suppose mass of an atom of hydrogen. This is 1.6736 into 10 to the power minus 24 gram. Mass of one atom of hydrogen is 1.6736 into 10 to the power minus 24 gram. Question says find the relative atomic mass of hydrogen. Means you have to express in terms of unit. So exact mass of one atom of hydrogen is given as 1.6736 into 10 power minus 24. Now what is the relative atomic mass of hydrogen? Means what is the mass of one atom of hydrogen in terms of unified mass. So look at this, is the exact mass. This is defined as absolute mass. So therefore look at this. we have this formula: absolute mass is equal to relative atomic mass into the gram equivalent of unified mass, that is 1.66056 into 10 to the power minus 24. Therefore, the relative atomic mass is equal to absolute mass divided by 1.66056 into 10 to the power minus 24. So this is in terms of U. So exact is 1.6736 into 10 to the power minus 24 divided by 1.66056 into 10 to the power minus 24 U. So this comes out to 1.008. This is conversion from relative atomic mass to absolute, absolute to relative atomic mass. Number 4. Let's suppose mass of one atom of an element A, mass of one atom of an element A is 3.9854 into 10 to the power minus 23 gram. Mass of one atom of any given element is found to be 3.9854 into 10 to the power minus 23 gram. Then question says, how many atoms are present in 1 gram of A? Mass of single atom is 3.9854 into 10 power minus 23 gram. Total mass of A is given as 1 gram. So how many atoms are present in 1 gram of this A? So total mass, look at this, total mass is given. So total mass is equal to mass of single atom multiplied by number of atoms. So this will give the total mass. So therefore, number of atoms is equal to total mass divided by mass of single atom. So total mass is given as 1 gram. Mass of single atom is 3.9854 into 10 to the power minus 23 gram. So this is 10 to the power 23 divided by 3.9854 atoms. So this mass of atoms is present in 1 gram of A. Now one more problem. Problem number 5. Problem says, if U, that is unified mass, were defined to be 1/5 of the mass of carbon 12. So look at this is a question. If unified mass were defined to be 1/5 of the mass of carbon 12 isotope, what would be the mass of nitrogen atom on this scale? That is a new scale. Atomic mass of nitrogen in the conventional scale is 14. So question says the conventional scale, that is 112 times mass of carbon 12, mass of nitrogen is 14. But if this scale is to be changed to 1/5 of the mass of carbon 12, then in this new scale, what will be the atomic mass of nitrogen? So now look at this, we have to change the scale. Let's suppose, look at this, W2, that is W2, be the mass of one atom of nitrogen, and this W1 be the mass of one atom of carbon 12. So let this be the mass. So according to this conventional scale, that is 14. This is equals to mass of one atom of nitrogen divided by 112 times mass of one atom of carbon. So this is equals to 12 times W2 divided by W1. That is the conventional scale. That is the equation 1. Now the scale is changed to 1/5 of the mass of carbon 12. Let the mass of one atom of nitrogen in this new scale be A. This A is the mass of one atom of nitrogen in the new scale. So this will be equals to mass of one atom of nitrogen divided by 1/5 of the mass of one atom of carbon 12. So this is equals to 5 times W2 divided by W1. So change of conventional scale does not change this mass. This will remain as it is. So we have two equations, and for this we have to show this unknown value. Now take this ratio. So taking ratio of these two, now equation 2 divided by equation 1, we take A divided by 14 is equals to 5W2 divided by W1 divided by 12 W2 by W1. So W2 you can say 1. So this is 5 by 12. So therefore A is equals to 5 into 14 divided by 12. So this is approximately 5 point something. So this is the mass of one atom of nitrogen if the scale was changed from 112 to 1/5 of the mass of one atom of carbon 12. So this is coming 5.83 in the latest or the change convention. So this is how we define different types of mass, and if the conventional scale is changed, how we can convert this into new scale, what are the relationship between the different types of mass, what is the meaning of atomic mass, what is the significance of each and every mass that we all use in chemistry. So this is all about mass of single atom. So once we know the mass of single atom, we can measure any mass of any number of atoms. So this is about atomic mass. So with this atomic mass, we'll conclude to this lecture that is based on atomic mass. Thank you all. So having gone through atomic mass, we are going to discuss molecular mass. The only difference is, in case of atomic mass, we define the mass of atoms, but whereas for molecular mass, we'll define the mass of molecule. So, first, that is the relative molecular mass. So, this relative molecular mass is defined as mass of one molecule divided by 1/12 times mass of one atom of carbon 12 isotope. So, similar to relative atomic mass, relative molecular mass is defined as mass of one molecule with respect to mass of carbon 12. So, this is again the ratio of two mass. So, relative molecular mass is again a simple number with no units. Again, look at this, 1/12 mass of one atom of carbon 12 is defined as 1 U. Therefore, look at this, relative molecular mass is equals to mass of one molecule divided by one unified mass. So, therefore, mass of one molecule is equals to relative molecular mass into one unified mass. Second mass that we use for molecular mass determination is absolute molecular mass. So, absolute molecular mass defines the mass of one molecule, that is exact mass of one molecule of a substance expressed in gram unit. So, this absolute mass, that is exact mass of one molecule, is equal to relative molecular mass multiplied by the gram equivalent of unified mass, that is 1.66056 into 10 to the power minus 24 gram. So this is the exact mass of one molecule, that is absolute molecular mass. Then there is one more mass, that is gram molecular mass. This gram molecular mass is simply also known as molar mass. So, gram molecular mass. So, again we have to look at this a gram molecule. So, similar to gram atom, 1 gram molecule is equivalent to 6.02 into 10 to the power 23 molecules. So, this is nothing but Avogadro number of molecules. So, 1 gram molecule, that is 6.02 into 10 power 23 molecules, is also known as 1 mole. So, the mass of 1 gram molecule, that is 6.02 into 10 to the power 23 molecules, or simply mass of 1 mole molecule expressed in gram unit, that is defined as gram molecular mass. So therefore, look at this, gram molecular mass is equals to absolute molecular mass into Avogadro number, that is 6.02 into 10 power 23 molecules. So this absolute mass is equals to relative molecular mass into 1 by Na. 1 by Na is equals to 1.66 into 10 to the power minus 24 gram, that is gram equivalent of unified mass multiplied by Ma. So this equals to relative molecular mass in gram unit. So gram molecular mass and the relative molecular mass both are having same numerical value but difference of units. So this is molecular mass. So all, again, if suppose question says what is molecular mass, so definition should be molecular mass is defined as the mass of one molecule of a substance with respect to 1/3 mass of one atom of carbon 12 isotope. That is defined as molecular mass, or simply relative molecular mass. This is absolute molecular mass. This is gram molecular mass. Now, from calculation point of view, example, suppose we have looked at this H2O molecule. So we have a molecule that is H2O. Now we have to find the molecular mass. So one molecule of hydrogen oxide, that is H2O, contains how many atoms of hydrogen? 2. So therefore 2 into atomic mass of hydrogen plus 1 into atomic mass of oxygen. So therefore this is equals to 2 into 1, atomic mass of hydrogen is 1, plus 1 into 16, so this comes out to be 18 U. So the relative atomic mass is simply summation of the atomic masses of all the atoms present in a given molecule. So if this is the relative molecular mass, then absolute molecular mass of one molecule of water is 18 into 1.66056 into 10 to the power minus 24 gram. Then gram molecular mass, that is mass of 1 gram molecule, or mass of 1 Avogadro number, or mass of 1 mole molecules of water, that is equals to 18 gram. So this is how we define molecular mass. So molecular mass is nothing but mass of one molecule. So take this. Let's define glucose molecule. C6H12O6. Now we have to find the relative molecular mass. So relative molecular mass, that is 6 into gram atomic mass of carbon, that is 12, plus 12 into atomic mass of hydrogen, that is 1, plus 6 into atomic mass of 1 oxygen, that is 16. So we have looked at this 72 plus 12 plus 96, that is 180U. So the relative molecular mass of glucose molecule, that is C6H12O6, is 180U. So therefore absolute molecular mass of glucose, that is 180 into 1.66056 into 10 to the power minus 24 gram, and the gram molecular mass of glucose molecule is 180 into 1.66056 into 10 to the power minus 24 into the Avogadro number into 10 to the power 23 gram. So this comes out to be 1. So that is 180 gram. So if any given molecule is given, then to find the molecular mass, you have to just add the atomic mass of the given atomic mass of all the atoms present in a given molecule of the substance, that is molecular mass. So in while defining molecular mass, there is no average molecular mass because molecule exists as a single independent identity, whereas atoms can exist in more than one isotopic form. Molecules does not show isotopic form, so there is no average molecular mass. So while defining molecular mass, either we define in terms of relative molecular mass, absolute molecular mass, or gram molecular mass. So this is molecular mass.